This video is about the path that light can take between two different materials, and it's with the view to be able to understand the prism in our optical scanner. So with that in mind, our two materials are going to be glass, which is the material in the prism, and air. And so in our optical scanner, the prism is set up as follows. And you have a light source here, and then you have your other components of the optical scanner coming off here. So this is glass, and glass has a refractive index of around 1.3, so we're going to call that N1. And then this is air, and air has a refractive index of around 1, so we're going to call it 1. Now, they have different refractive indices because glass is more optically dense than air. So light actually travels slower in glass than it does air. So you can see how that affects their refractive index if we look at the equation N equals C over V. So here, C is the speed of light, 3 times 10 to the 8, and V is the velocity that light travels in that particular material. So obviously, if light is travelling slower in glass, it's going to lead to a higher refractive index. Great. So now we've got that sorted, we're going to go on and have a little look at the back at the diagram, because we want to be able to find some sort of equation that describes the path of light. Now, luckily, there is an equation for that, and that equation is Snell's law, which is as follows. So Snell's law states that N1 sine theta 1 equals N2 sine theta 2. Now here, theta 1 is called the angle of incidence, and theta 2 is called the angle of refraction. But what on earth does that mean? Well, let's have a look back at the diagram. So I'm going to draw a normal on my prism, which is a line that's perpendicular to the interface between the two materials. And then this is my incidence ray. So this is a ray of light coming in from our light source here. I'm just going to extend the normal. And then this angle here is theta 1, our angle of incidence. Now, you might expect that light would just continue on its path sort of up here somewhere. But when light travels from a more optically dense material to a less optically dense material, the light is actually bent or refracted, and it is refracted in such a way that is away from the normal. So this is theta 2. Now, that does work in the opposite direction. So conversely, if you were going from a less optically dense material, i.e. air, to a more optically dense material, i.e. glass, then your line, which you may expect to come down here, bends towards the normal, so therefore comes down here instead. Great. So what relevance does this have to our optical scanner? Well, in order to understand that, we need to develop this concept a little bit further. So if you increase theta 1, you increase theta 2 as well. And if you increase theta 1 so much, you become to a point where theta 2 is actually perpendicular to this surface. So I'm just going to draw that on here. So we've increased theta 1, so now it's coming somewhere here. And as a result, this is theta 2, and it's now at 90 degrees. So what does that mean in Snell's law's equation? Well, theta 2 is at 90 degrees, and sine of 90 is 1. So this equation now collapses to N1 sine theta 1 equals N2. In order to find theta 1, we just divide N2 by N1 and take the sine inverse of it. And if we plug in our numbers, i.e. air was N2 at 1 and glass was N1 at 1.33, then we get that this is 42 degrees. And this angle we call the critical angle. So why do we call it the critical angle? Well, it's because if you have any angle that is greater than this angle as your incident ray, this ray of light no longer comes out into the air, it gets reflected back into material 1. So let me just draw that on here. So imagine this was bigger than our critical angle. Then you'd get a ray of light coming down here, and this would be your theta 2. And this is how our prism in our optical scanner works. We do need to add an additional concept in, which is called frustrated internal reflection, which is quite misleading because it's not really a reflection at all. I'm just going to clear some of this space on the board. So, with frustrated internal reflection, imagine you have the same setup as before, but now we put a third material in here, and this material has a refractive index N3, and N3 is larger than N2, where you remember that N2 was the refractive index of air. Now, if this is true, and this gap is very small, and by very small I mean less than a couple of wavelengths of light, then something quite interesting happens. Instead of getting what you might expect, which we just discussed, which is this kind of total internal reflection, at this boundary here, there's something that is similar to quantum tunneling, where the light hops this gap and just continues in through this material 3 here. Okay, so now we've gone through all that, you may be wondering, okay, what on earth does this have to do with this prism in the scanner? Well, I'd like to draw the prism once more, and this is a very crude representation of the values in your finger and the ridges in your finger. So again, we have the light source here, and we have the other components here. Okay, now, if the light hits a valley, then it is totally internally reflected, because remember, this is air and this is glass. However, light can also travel to this part, where it hits a ridge. Now, the gap between the ridge and the glass can be considered to be smaller than a couple of wavelengths of light. So instead of it being reflected, it just gets absorbed into the skin. So no light reaches the other components from here. And then with the buildup of light intensity on these other components, you start to form an image of what the original fingerprint may have looked like.